With greater coordination spheres, we have greater elements of symmetry that are present in our molecules. Symmetry is one of those things that you probably have an idea of it when you see it, right? You've heard about symmetrical faces and other symmetrical objects. But what we need to do is we need to define some tools that allow us to discretely define the symmetry operations and elements of a given structure. Now, for this section of the course, we're going to be using molecules quite a bit to discuss this, but eventually you'll start seeing symmetry in everyday objects and you can start practicing these symmetry operations on things that you find around your house or while you're out and about. So the first thing is defining what we are going to call a symmetry element, right? So symmetry elements are our first kind of definition here. Right. And symmetry elements are just a point of reference for operations, right? So points of reference for operations. Now, it's always bad form, right, to use a word that we're going to define, like operation, in our current definition. But a symmetry element just describes one of three different things. So it's either a point, an axis, or a plane. Right, so these are all kind of mathematical terms that describe the location of a molecule, the location of an object. And then we're going to see what we do with these when we talk about operations in a second. So when we talk about a point, we are almost always talking about the origin. So we're going to be drawing lots of these three-dimensional axes, right? So we have X, Y, and Z. And so when we talk about a point, it's almost always just going to be the origin. Right, and we are going to center our molecule on this origin point. And so our essentially whatever central atom we have is going to have coordinates that are 0, 0, 0 for the center, right? That's what we mean by the origin. When we talk about an axis, it could be our X, Y, or Z axis itself, right? So we could be talking about our X axis here, right? We could be talking about our y-axis, but we also have axes that might not lie along the coordinal or the main axes, right? So we could have an axis that splits, right, the xy plane, right? So we could have some kind of another axis that doesn't lie directly on one of these points. But the important thing with an axis when we describe it is that it is essentially a line, right? And lastly, a plane. A plane is defined by two axes, right? So again, if we have our x, y, and z kind of coordinates, and we were going to draw a plane, right? We could draw our plane, in this case being the YZ plane. We could also try to draw out, in this case, our XZ plane, right? And there's also our XY plane. And so these are the points of reference that we're going to use for symmetry operations. So again, we have points, axes, and planes. And these are what we call the symmetry elements. And these are what the symmetry operations occur over. So let's actually talk about some molecules, right? Let's build some molecules and think about how these symmetry elements and symmetry operations come into play. So our first example that we are going to look at is actually platinum tetrachloride. Right, we're going to give it a 2- charge. And part of the reason for this is that we want this to be a square planar complex. So we haven't talked about what makes something a square planar complex, but maybe you've noticed the pattern so far. If we have a 4-coordinate complex that is D8 and 16 electrons, square planar becomes a electronically favorable coordination. So this will be our square planar complex, and we're going to use this example to describe our symmetry operations. All right, so this is where we're going to start bringing in operations. And so a symmetry operation, right? A symmetry operation is a motion or action, right? It's something that we are physically doing, right? We can think of operation like doing something about a symmetry element. Right? So this is where we do something or we manipulate our structure about one of those different symmetry elements. So we move it or we manipulate it about a point, like the origin, or we move it about an axis, like a rotation, or we can even reflect it, like through a plane, right? So we have operations and we have elements. So let's connect those here. So we had three different elements. And so now we're going to see what kind of operations occur on those elements. So we had a point, we had an axis, and we had a plane. So points are going to have inversions, right? This is the operation that we can do upon the symmetry element that is a point. An axis is going to be rotations, right? We rotate about an axis. And a plane is going to be reflections. Right? So these are the actions that we take about these symmetry elements. And again, we're going to use this platinum tetrachloride as our example. It is a square planar complex, right? It is a square planar complex. Here is that tetrachloroplatinum complex. So I've made this in Avogadro and the mole file is posted on Canvas. So if you want to try to manipulate this or follow along by rotating and moving this molecule about, if this helps you get a better sense of the three-dimensional orientation of the molecule, now you know where you can go and find it, right? This is posted on Canvas. You could even build this based on the kind of skills that we developed in our last lab meeting. So you might want to practice using Avogadro for building and manipulating these structures. It'll be really helpful throughout our symmetry discussion. So let's start defining some of these symmetry operations for our platinum tetrachloro compound. So in order for something to contain an operation, right, if something contains a given operation, the structure, and again, it's not necessarily molecule, right? Symmetry operations exist for things outside of molecular systems as well. The structure must be indistinguishable from the initial state. So what we're defining here, right, is these motions or actions that we can perform on a molecule that leaves a structure that is indistinguishable from its initial state. So let's look at our compound, and we're going to start with what we call a proper rotation. Right, this proper rotation is our first symmetry operation. And these get the label, or these get the name C with a little subscript n. And this n describes the axis that we're going to be going about. And so we'll see that in a second. So let's look at our compound. So we have our platinum that is square planar with these 4 chlorines. And it has a 2- charge. I'm not going to draw it on there because it might get confusing with our kind of symmetry discussion here. But what I'm going to do is I'm at least going to follow this particular chloride, right, or chlorine that is circled with this pinkish color. And again, a rotation occurs about an axis. And so what we need to do is we're going to define our axis here as the one that is sticking out of my drawing surface. Actually, I'm not happy with that. There we go. So this is going to be my axis that I'm going to do a rotation about. So I'm going to spin my molecule about this axis, right? So if I imagine I poked it with a fork, now I'm going to twist the fork. And what I'm going to see is that this molecule, right, can rotate 90 degrees. And when I do this 90-degree rotation, if I were going to redraw my structure, platinum still has its 4 chlorines, only now my pink chlorine is over here on the right-hand side. Now, if I didn't circle it with that pink circle, it would be indistinguishable from my initial starting point, right? So therefore, this is a symmetry operation that is present in this molecule. And how we define this, right, this value of n, is that we would call this a C4 rotation. It is a proper rotation. We're going to talk about improper rotations soon, but for right now, we're only looking at proper rotations. So where does this 4 come from, right? It is, if we did a full rotation, 360 degrees, divided by, right, whatever rotation we actually did. So in this case, it was 90 degrees, right? So this is where we get 4 from. The other way you could think of this, right, this value 4 here, you could think of this as the number of rotations that takes you back to where you started. Right, so if we did this rotation 3 more times, we would end up back where we started, right? So we could do another C4 rotation, and it would move that pink circle down to the bottom. A third C4 rotation would move that pink circle to the left. And that final fourth C4 rotation would take that pink circle back up to the top, right? And so this is our proper rotation. And it describes this just rotating about an axis, right? All of this relates back to the axis that we are looking at. So let's look at these in a little bit more detail. So what we're going to do is we're going to draw out these C4s, and we're going to kind of work through them one by one. All right, so that means we're going to do a lot of drawing on this slide. So we have our platinum with our 4 chlorides, Cl, 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 and Cl. And what I want to do is I want to look at these as these 4 different C4s and look at them in sequence. All right, so like I said, we're talking about these principal rotations. I'm going to circle one of my chlorides just to make it easier to see. I'm talking about my C4 rotations that are occurring along this axis, right? So this is what we are describing. We're talking about the C4s, about this axis that is sticking out of the plane of my drawing surface. So this first C4 rotation that occurs, right, moves my chlorine here to the right-hand side. If I imagine that I do another C4 rotation, this brings my chlorine down to the bottom. And now this is where we're going to start to introduce some new kind of terminology or new ways of describing this. This was my second C4, right? So I'm describing from where I started to this point. It would be 2 C4 operations, right? The first C4 operation brought the chlorine to the right. The second C4 operation brought that chlorine down to the bottom. Now, what you might have noticed is that this rotation is actually what we call a C2, right? If we had rotated this molecule 180 degrees from where we started, this would be a C2 rotation. And in fact, we always want to use the lowest number that we can to describe one of these rotations. So far, we would say that there is one C4 operation, right, that we can account for, and then there is one C2 operation that we can account for that occur along the same exact axis, right? Operations occur about an element. So this same axis has a C4 and a C2. If we undergo another C4, now we end up with our pink chloride that is on the left-hand side. This does not have another or a lower number that we can use, right? If we're going to calculate this is our third C4. So we did 3 of them to get to this point. So this is now a new unique symmetry operation to get to this point. So this is our second official, right? So our second C4 operation. Right. You sometimes might see this referred to as the counterclockwise operation, right? We can see that we had one C4 that occurred from a clockwise, and this was a unique operation, was our C4. When it occurred to our counter, or when it went counterclockwise, we ended up here, right? Where the chlorine is on the left-hand side. And so far, if we're keeping a list of all of our symmetry operations that we've described for this molecule, we would have 2 different C4s so far, and so far we would have 1 C2, right? And these are proper rotations that we've described. So we want to keep kind of a running list here for this molecule. But like I said earlier, what if we did one last C4? So what if we took this molecule back up to where we started? Right? So this would be essentially that fourth C4, right? So C4 to the fourth, what happens? This has a special name, right? This is called E, which is the identity. Every single molecule, when we are describing the symmetry of a particular molecule or structure, has the identity, right? This is the mathematical equivalent of multiplying by 1. Right? When we multiply something by 1, it retains its identity. And so this is another symmetry operation that is present in everything. So everything we ever look at will have an identity. So we have our C4 here. This is our highest value that we, or of N, that we have for this molecule. And so for this platinum tetrachloride, C4 is what we call our principal rotation axis. So let's make sure we define that, right? So we have principal rotation axis, right? And this is the axis that contains the highest value of N. In our principal rotations, right? So the highest value of N that we have for our platinum tetrachloride is 4, and so that would be our principal rotation axis. The convention is, right, so I'm going to write that the convention is that your principal rotation is your z-axis, right? So when we draw these molecules, you would draw your principal rotation as the z-axis. So if we were going to redraw our molecule, right, we would want to put these chlorides along our x and y axes because our z-axis, which is our principal, should contain our C4 axis. So if I was going to redraw this, draw out my nice, and that's being a little bit sarcastic, right? I'm not exactly an artist here. We would put our platinum at the origin in the center. We would put our chlorides along my XY axes. And then that leaves my z-axis here for my principal rotation axis, right? So when we describe our principal rotation axis, it's this one here. And so this is a normal convention is we label the axis with this highest rotational value that we have. And yeah, so this is where we see our C4. And we know that this axis contains also a C2. So we could describe this in several different ways. Now there's other different C2 axes that we could draw here. So this is our principal rotation, but what other proper rotations do we have? So let's pick another color here, maybe a nice blue. We'll see that we actually have other C2 axes, right? So we have one that bisects our axes. So if we rotate about this axis, we would see that we can exchange our chlorides in the same kind of way. So this axis runs all the way through, right? So this is a C2 axis, in which case these two chlorines, right, would switch places. And these two chlorines would switch places, right? We also have another C2 axis that lies along each of my coordinates. Right, so this picture is getting awfully messy, but this C2 axis contains two of the chlorines. And so if we perform one of these C2s, so let's say we perform this one that is here along my y-axis, right, or is along my y-axis, my chlorides along the x-axis would switch places, right? So this again takes a little bit of getting used to. I'm going to introduce some resources that help you visualize this. But if you have a model kit, if you build this in Avogadro, I'm gonna really highly recommend that you do that so you can see these principal rotations. So again, this is what we describe as a principal rotation. Is one of these things that occurs about an axis. And the after one of these operations, it is indistinguishable from where it began, meaning we have these four chlorides and they end up in places that look like where we started. But we know better, right? You and I that did the operations actually know better. So we've labeled what the identity is, right? This is that kind of like do nothing operation, right? It's the mathematical equivalent of multiplying by 1. And we've identified these proper rotations. So these are essentially just grabbing the molecule and rotating it. So let's talk about a reflection next. So if we go back and we look at our list of elements and operations, there we go, we can see that reflections occur along a plane, right? So our element that we're looking at for a reflection is a given plane. So let's draw our molecule out again, and let's talk about these reflections that are present. So I'm going to keep using the convention we just talked about, where we use the z-axis as our principal rotation. So I'm going to kind of redraw my molecule to make it look almost like it fits along the x, y axes without directly drawing these axes, right? So we can always kind of imagine that in the corner, right, we have our little axes to help orient ourselves. We have x, y, and z. And so now what I want to do is I want to be looking at reflection. So this is going to be the next symmetry operation that we are going to dig into is reflections. So we have several different things that happen here. So a reflection is like looking in a mirror. And when we look at a reflection along a plane, what we're doing is we're saying, if we were going to take this molecule, right, and draw out a plane, right, in this case, this is my XZ plane. My chlorides, right, when they look in the mirror, they're going to see each other reflected across this plane, right? So I'm actually going to choose a different color there for it. I didn't want to do that. So still looking at that same plane. And here's our chloride. And let's use blue. All right. And when we undergo this reflection, And reflections get the label sigma, right? And we can put a subscript to describe the plane. So this is a reflection along our xz plane. In order for this to be a symmetry operation contained by our molecule, the final state has to be indistinguishable from our beginning state. But if we were able to track these, what we would see is that the pink and the blue chlorines essentially switched places, right? If we did this reflection, if we moved everything across this plane, we would see that the purple or the blue and the pink chlorines switched places. And the other chlorines are inside our plane, and so these are unchanged. Right? These didn't move. Okay, so this is a reflection, and we have several different reflections. So we have a reflection in the XZ plane. And what I'm going to challenge you to do is, if you have this open in Avogadro, is that I want you to find some of these other reflections, right? So there's also a reflection in the YZ plane, okay? And there's even a reflection that dissects the X and Y planes as well, right? So how many other reflections can you find? All right, we're going to talk about visualizing these in a little bit. I just want to build up some of these kind of fundamentals so we can continue practicing with them. So what you'll notice is that this reflection that I've drawn, this XZ reflection, if I'm going to go back and draw in my principal rotation, right, this is along my Z axis, was my C4, we can see that this particular reflection, so sigma XZ contains my C4 axis. Right? Sigma xz contains my C4 axis. And this is going to be an important designation because when we have a mirror plane that contains our principal rotation axis, this is going to be a vertical mirror plane, right? Which is also referred to as sigma v, right? These contain our principal rotation axis. There's also another label, and we'll talk about this more when we get some practice where we can see it, that is sigma d. These are dihedral, and these also contain our principal rotation axis. So by contrast, right, if I'm saying that this is a special type of mirror plane, then we have to have something that doesn't contain our principal rotation axis. So let's look at one more reflection here. So again, we're going to redraw our platinum. We're going to draw it suggestively along our set of axes here. And what we're going to identify is that there is a plane here that contains all of our atoms, right? And so this is our XY plane. That if we did a mirror image, right, if we were going to slice this molecule along our XY plane, we would see that none of our atoms move, right, but they all can be reflected across this plane. And we know that our z-axis, right, is our principal rotation here. So this plane does not contain, right, so this sigma xy does not contain our principal rotation axis. Right? In fact, sigma xy is perpendicular to our principal rotation C4. So this gets a special name, right? This is now sigma h, where the h stands for horizontal. Right? The H stands for horizontal. And in a given structure, you can have multiple vertical and dihedral mirror planes, but you can only ever have a single horizontal mirror plane. right? So you cannot have more than one sigma H. It is either there or it is not, right? It is either there or it is not. So now what we've done is we have covered, or at least introduced, the identity, proper rotations, and reflections. So we have one more here that we need to talk about, and that is an inversion. So again, inversions occur over a point, right? So when we think inversion as our operation, this goes over the element of a point. And this is, again, generally the origin, right? 0, 0, 0. So we draw out our molecule. And what an inversion point does, right? Again, this is our origin is at the center of our platinum here. For an inversion, each one of our atoms travels through the origin and out the other side an equal distance, right? So for an inversion, everything moves through the origin and out the other side. So if we're going to identify one of our chlorines, so let's change our color here so we can follow it. Let's say this chlorine here, it's going to travel through the origin and out the other side. Right, so when I draw my new complex, right, after I get this inversion, which gets the italics I, is our label for this symmetry operation. That chloride that I've described in blue ends up here, right? It moved through the origin and out the other side an equal amount. While at the same time, right, this chloride moved through the origin and out the other side. So it ends up here. Every single one of our atoms does this same process. Through the origin and out the other side. Through the origin and out the other side. So this molecule or this structure does in fact contain an inversion center because this operation exists, right? All of our atoms can move through the origin and out the other side an equal distance and end up with a structure that is indistinguishable from where we began, right? So now let's take inventory of what we've done. We've talked about what an identity looks like. We've talked about proper rotations. We've talked about reflections, and we've talked about inversions. So at the very least, what we've done is we've defined these things, right? We don't have an exhaustive list yet of every symmetry operation that exists for this given compound, but we can start to define them and start looking for them, right? Now we have the tools. Now it's time to actually put them into action. So what we're going to do is we're going to have a problem set and some files that we're going to look at in our next class where we can try to help visualize these different types of symmetry operations that occur upon these symmetry elements. In the textbook, right, so in Miesler and Tarr, chapter 4 is all about symmetry. Right, so the first few sections of the textbook have lots of good pictures that help us define symmetry that might help you see these elements and operations a little bit easier. We're going to do more practice on these in class, right? Our goal right now is to understand how these operations occur, and we'll do more practice so we can kind of see them in action. Again, don't be afraid to build some of these things in Avogadro. I think it's a really helpful way to show these manipulations as they're occurring, right? Actually being able to rotate and think about these molecules in 3 dimensions. All right. So again, read up on Miesler and Tarr, do a little bit of practice in thinking about how these things work, and we'll do some practice in class together in our next meeting where we talk about how we can use these symmetry operations and kind of build more of an exhaustive list of all the symmetry operations that are present for this particular compound.